Cheers, guys. I'm Kyle. I'm from Plymouth, University of Plymouth, down in Plymouth, of course. And this is my actual first lecture I'm giving. So if I'm a bit wobbly at all, anything like that, just, kind of bear with it if you can. Thanks. That'll be a huge help. Anyway, so a bit about myself. I'm a geomorphology student, currently coming to the end of my bachelor's degree. At the moment, I have been heavily focusing on climate change as well, geomorphological processes, landscape evolution, sort of those kind of processes. And basically, I've always had a general interest in Mars. One of my key hearts, I've always had a passion since I was very young, was always down to space. I always had a huge interest, just been generally fascinated in that sort of field. And it's just been a very, very key part of my life. So it was very interesting when I was coming to decide what I wanted to do for my dissertation. I had no idea, kind of wanted to go down the geomorphology route, kind of want to do geography aspect, something in that field. And one of my friends mentioned to me that a professor at this university was focusing recently on Mars, and more focused on dunes. And this professor has actually just recently been in the news back in the summer, because he was the guy who discovered dunes on Pluto. And funny enough, he's only had about a few years' experience in remote sensing dunes. So he's just, he's kind of taken on this role. He's absolutely loved it to bits, and basically it's kind of shown. And this sort of enthusiasm then fed onto me to come and become a, studying dunes as a whole. And I've just basically loved the entire experience. And basically my lecture today is just running through what I did for my dissertation, but then also a bit about the surroundings of Mars and what I had to kind of learn, and, the experiences and the history. So I'm going to run through some general stuff, background stuff about Mars as a whole. Introduction, quite a few of these facts you might know, a few of them you might not know. So basically, fourth planet from the sun, of course, that's the basic fact which a lot of people learn quite a young age. They're quite fascinated. It's one of these key bits about Mars. But looking at more of a landscape aspect of it, there's only about the same sort of landscape on Earth and Mars, size-wise. They're both pretty much bang on exactly the same in that whole general understanding and that aspect of landmass coverage and all that. So if you took all the landmass of the planet, of Earth, it's going to be roughly exactly the same as that found on Mars. Distance-wise, it's quite a vast distance, actually. And when you think about it, not a lot of people realize the actual scale of how big the actual distance. For example, if I had the size of a grape, if the Earth was the size of a grape, Mars, on average, would be located, I don't know, about 2 football fields away. So that just puts in perspective how huge of a distance the actual aspect is. And really, the first actual written record of Mars was about 4,000 years ago. That we know of course. There may be records we don't know, but generally Mars has been a big, huge influence in human civilization, beliefs, mythology, study, astronomy. So for many, many years, it has been a key part. Oh, hang on. So this is the geological map of Mars, and here's a question: how many of you have seen the film The Martian? Good amount of you. Cool. The Martian took place just about here on this map, and where he had to travel to was this crater right here called the Shapley crater, around about here. My field site was just here, so not too far away, but a good distance away. So that film kind of was one of the reasons that got me really passionate about this actual project and why I wanted to do Mars as such. And it's that kind of inspiration that kept snowballing until I did all the research for it, and we just absolutely loved it. But the key geology here is you've got these volcanic intrusions here. Mount Olympus Mons is just about there. And the key bit for this actual talk is this green layer right here. This green layer is a sandstone, is sedimentary deposits. And a lot of it has been eroded through over time, mostly through atmospheric conditions. So it's not a huge amount it's not a huge amount in the sense that how much sediment's there. But it's just basically a top layer. And this top layer the data for this top layer came a lot from this probe right here. This is the Phoenix probe. And this probe, about 10 years ago about 5-6 years ago landed there. So it's a key probe, and it's basically given us a lot of data about what the soil composition is. And back to the previous map, the Phoenix probe is up this same altitude here. So when it came to understanding what the actual soil composition was, it was a very, very good bit of data to know what the actual soil was. And given it's the same lithology, it's pretty much assumed that it can be the same. And here, if you look up here, this is the geological timescale of both Mars and Earth. So the dinosaurs went extinct right about here. So it just shows you how vast this timescale is for Mars in retrospect. It's just quite a vast distance. And you can see a bit of the arm here. This is a photo from Mars probe. This is the CGI ARTHUS model. This is geomorphological history of Mars. So about 4 billion years ago, 4 billion years ago, this is what Mars would have looked like. There's a big theory at the moment that the entire region where the dunes, the northern polar region, was a giant ocean. And this ocean occurred around this period here, this era, where a lot of the erosional and landscape evolution, the rivers and hydrological aspects came from this whole period. And as you can see, over time, the amount of processes sort of dwindled. The amount of features being developed, the amount of basically the amount of activity occurring on Mars sort of dwindled as more and more it went on. And basically, it just eventually kept going until eventually there was only little amount of geomorphological activity. So dune formation, atmospheric erosion, maybe a little bit volcanic activity, but that kind of dwindled as basically the planet just basically died as such in a quite informal terminology. So, okay, no, oh jeez, sorry about this, guys. You got better than me in this. Just trying to get working. Oh.
The button below that changes the most, that might be it.
Okay, hang on.
Press the little button below it.
Yeah, this is. Oh. No, it's not that button. Oh, there we are. It was just the button basically playing that, basically. To understand what the dunes here were, there's a key bit to understand, which is the actual satellite, which was basically used to detect this. And the actual probe used was called a satellite called the Mars Orbital Reconnaissance, the Mars Reconnaissance Orbiter, which basically had a device on it called the HiRISE, which is the High Resolution Imagery Science Experiment, which was this camera right here. And basically it was a joint project between NASA, JPL, it still is, joint project between NASA, JPL, and Arizona University, which they tried to map out Mars, basically, using a really high-def camera. And this camera could measure to 25 centimeters pixels. So hypothetically, if you were laying down on let's say you were laying down on Mars, if you could, it would basically be able to pick up your hand. That's how high detail this camera is. So it's valuable for understanding the actual scale of it all with dunes. And so it's a very, very important measuring technique. And what we can do is we can actually obtain some images like these. All these different images are taken by HiRISE. So if we run through them, you've got some craters here. As you can see, there's dunes located. How many of you have heard the face of Mars? Okay, a few of you, cool. Which was basically, back in the 90s, they discovered a photo on Mars, and it looked like a face. So they all believed alien activities and stuff like that. This is the same feature, what it actually looks like. And as of course you can see, it was just down to resolution. So you can see how vital resolution is for misconceptions, for understanding key bits. And it's just important that we have this high detail, or we're going to miss out key bits. But if you're wondering what the different colors are, they're different bands of light. So if you look through it, different lenses, different wavelengths of light, that's basically, simply put, what you get these different features standing out. And this is key, this sort process is part of the remote sensing process. And it's this key understanding bit, which is what is needed to understand what's happening, basically. And the actual photo I'm quite fascinated by, I like quite most, is the avalanche here. You can see this detailed avalanche of, and this is just basically catching an avalanche in action, which is quite impressive. But the other one, which is really, really, really impressive, if I have to say, is this one here. And if I expand it, this photo is, you might have seen this, is of a landing. And basically, just by chance, I think it was like a 0.002% chance, just at the right time, at the right place, it caught this probe. This probe you've just seen. This was this probe right here. And this probe here, basically, by chance was caught. And it's showing you basically what happens when, it's just basically showing you that sort of space, in that sense, like in a spatial aspect, in a place sort of scenario. So you kind of picture where everything is in place. It's quite a fascinating photo, actually. But anyway, moving on. So that's just some background stuff on Mars as a whole. Some key bits, some general history, some general... So it kind of speeds you up a bit. It's not highly detailed, but at the same time, it's just kind of giving you a run through since we're on time. And this man, when coming to dunes, is a really fascinating bloke. He's basically arguably the grandfather of dunes. Ralph Bagnold, former brigadier, explorer, geologist. This guy fought in the North Africa campaigns in World War II. And his passion was never for commanding, though. His passion has always been for dunes. This guy, for all his life, was obsessed with how dunes formed. He was so obsessed, in fact, he actually built a wind tunnel at the bottom of his garden. You know, just by hand. And at that time, when studying these dunes, he came up with two key formulas, which was his Bagnold formula, which is used as an equation which is constantly used even today in understanding how dunes form. And this equation is basically the equivalent of Einstein's E equals mc squared principle in understanding dunes. And he did this all through himself. And at the same time, he also developed a constant, a number. Don't ask me what the number is, I can't remember off the top of my head, but it's a very key bit, actually. And so this guy laid the groundwork in his book, Physics of Blown Sand Dunes, and this book is heavily still referenced today. It came out in 1941, but it's still referenced today. The work it laid down, crucial in understanding what happens. And funny enough, originally from this part of the world, from Plymouth, funny enough, for his work as well, when he passed away, they named a dune field after him on Mars called the Bagnold Dune Field, and it's one of the heaviest studied, well, most studied dune fields on Mars. And a lot of the research done has been done in his name. So it's kind of nice how things kind of come full circle for the guy who never got to see this, but, you know, fascinating what he did. So dune structures. So dunes are quite odd in their way. They're heavily dominated by sediment, heavily dominated by the topography, how the land is shaped, but then it's also crucial on wind. Different planets have different wind speeds. Mars has much less wind speed, we'll come to this later, but has much less wind speed than Earth. And basically, dunes are crucial depending on the wind. So this is a cross-sectional image showing you how different angles, at a certain angle, the slip face forms, which is this key bit here, which is where the gravity, the weight of the actual dune is too much, and it sort of slides. This shows you the actual general how wind relates to the actual shape of the dune. And here is the different shapes you get from different velocities or speeds of wind. And this value means wind shear velocity, basically. So it's a value. This diagram right here, though, this shows you sediment in relation to flow direction. You then have how the wind relates to the actual dunes. And this one here shows you the elevation of the dune. So it shows you from a height from 0 to 10 on the scale. It shows you the height of the dune. So it shows you the topography as such. Here's a little funny cartoon as well, which is brilliant, showing you how different dunes. So, like I mentioned earlier, wind is much less on Mars. So if we compare, look at Mars, the plane can't fly very well because there's a lack of wind. Earth, it can fly, of course. You know, most of you have probably flown, so you haven't flown out the sky, I don't think. No? Okay. And this is the different pressures, basically, the pascals. So the different values. So Earth has about 101 kilopascals. Mars only has about 600 pascals. So hardly any wind pressure. So when people talk about, restoring to an Earth-like atmosphere on Mars aspect, probably not going to happen. The atmosphere was basically stripped away from continuous bombardment from the solar radiation, so from solar wind, basically. As you probably know from your previous lecture, which quite nice links in. And basically, the atmosphere is so low that it should be impossible that dunes should form on Mars. But yet it does. So why is that the case? Like, it shouldn't happen. And the reason to this is key process. Instead of wind playing a key role in continuously forming the dune, there's a splash effect which is called, It's called sublimation, which is basically where sand is ejected when a grain impacts it. So it's a bit like an asteroid. When an asteroid impacts, it injects material into the air. And this continuous injection of the sand is what actually helps these dunes form. So it's this key process. So instead of the wind playing a role, with the grains being lifted up by the wind, a single grain could be lifted and it can cause a chain reaction, which then in turn causes the sands to form and build up and over time form the dunes. So that explains how, despite the low pressure and the low wind speeds, there's still high amount of dunes. Mostly confined to craters in the polar regions, but we'll come to that. Oh, yeah, some's my luck today. Hang on. Oh, there you are. Oh, okay. I don't know if this is like playing. Oh, there you go. Cool. Okay. On. Okay, cool. I'll wrap this up quickly. So, all right. Here's a quick question, then, guys. Earth or Mars? Raise your hand if you think Mars is left. Okay. Raise your hand if you think Mars is the right. I can confirm most of you are wrong. It's that way. This one was actually taken from Google Earth and just grayscaled. This one was taken from Google Earth and grayscaled. But it shows you the detail, talking about the camera earlier, shows you how detailed the dunes are, in fact. So this is the sample site we looked at. Well, I looked at, but we looked at this sample site here, this dune field, in relation to the topography. And this diagram shows you all the different dune fields around the polar region. And this shows you different winds as well. It's kind of a bit out of focus, but these arrows here are the wind arrows. So what we should be expecting is wind coming from the northwest. So our main task was to try and break down what is happening on this dune field and work out how are these dunes forming in the way they did. Just generally looking at where the sediment came from, how the dunes form in relation to the mechanisms, how they are positioned, so the shape. So it's these key bits which we need to know. And these were the key questions answered. Why are the dunes present here? What are the presence of markings, these black markings, which are seen dotted around these dunes, which is another key bit which was interesting to us. What are the key differences between this and other dunes, both found on Earth and Mars? And what does the morphology tell us about the mechanisms? This is how they were divided up. They were divided up depending on the concentration of dunes at random. So this section was chosen because high density. This section was chosen low density. 3 with high density, 3 with low density. There's a bit of overlap as well, but that was down to time constraints, so we couldn't actually tidy up a bit. And these were the data we collected about it. The orientation, the black markings, which are vents, what quantity is it per dune, the quantity of ridges per dune, which is the slip face, the ridge at the top of the slip face, as I mentioned earlier, and what the size of the dune, so the footing. So these are the black markings here recorded. Their markings are orientation marked. The ridges, the actual axis of the dune is marked, which then we measured a couple of them. And we also marked out the horns as well. The ridge, by any chance, is this bit here, which is this sharp contrast. And over here is this beautiful diagram, multicolored, and it basically shows you the orientation of all these dunes. And all these dunes were manually mapped out, 1,300 dunes in total. And each orientation was marked out and color-coded, so you can kind of see similarities or differences in changes. This one was the markings. How did they compare to the orientation? Where we had a theory that the orientation depended on the amount of markings. And as you can see here, there's pretty much no correlation at all. There's pretty much dotted all over the place. It's kind of like somebody slapped it on. But it does provide a good color-coded section. So you can actually see there is some patterns here of like higher concentrations up here, which links into the larger dunes, which later we'll go over. But this R-squared value shows you how strong is the correlation. And this just basically shows no correlation. So 1 would be a perfect correlation. 0, no correlation. So here is we tried this again, but we compared the markings this time, instead of the orientation, to the size of them. This one is done using a computer program, which was developed using coding, which picked out pixels, the dark pixels, and then they were compared to the size of dunes, so each dune. And basically, it came to some correlation, but a very weak correlation. When we did it manually, though, so we took a select number of dunes, I think it was about 200, about 40. We then compared it at random, using the computer again, using coding, to randomly select dunes. The value came to about 0.89, which is a extremely strong correlation. So it shows you which one's better, human technology or, well, human ingenuity or actual computer analysis, because computers can get it wrong. And again, you can see the higher concentration up here especially, which is kind of showing that there's something going on up there. And then finally, we compared how do the area compared to the ridges. So the amount of ridges, so conjoined dunes, compared to the dune size. And there is some correlation, but it's a normal correlation. So there is a link in that sense. And once again, you can see bigger dunes up here. This is the orientation, though. This is the key bit when looking at the weather, the actual atmospheric conditions. As a whole, it's pretty consistent. Pretty much, I'd say 96% of the dunes axis, the orientation was pretty much exactly the same, in the same direction, so southeast direction. Couple to the south-southeast or couple to the east-southeast direction. And variation remained consistently, as you can see here. So these were the key findings observed from this. Dunes, there's a key supply of dunes up here, explaining why, with the literature and what's previously been found, why the dunes up here is a key size of area. There's the amount of markings is also down to seasonal attributes. So while there is no link in such saying the orientation plays a role, it is formed due to the amount of vents. Additional evidence shows that dunes are conjoining, as you can see from this here. As you can see, they're conjoining. So they're forming these barchanoid ridges instead of barchan dunes. And finally, they're heavily influenced by wind dynamics. So wind is still playing a vital role, but it's always down to other mechanisms in such. So how does this compare to what's been discovered before? As a whole, it's pretty much similar to what we've known. It just kind of reinforces the point of the research set out. So, for example, barchan dunes are observed on Mars, as well as Earth, but they're far more present on the polar regions. There's a dominant wind source, which is kind of unique because the wind, even though it plays a role, it's one directional, but there is some variation at times, as you can see from the vents. The amount of defined dunes is unique for the area. So the actual amount of well-defined dunes in the size is huge. And finally, the carbon dioxide vents, or the vents, are pretty well found. So what was the potential further work? The key problem we had with this is we didn't have a second photo. There was only one photo taken of that site. If we were to do future work, the best way we could do it is request a potential second image and compare it and see how it's changed over years. Because that photo was taken back in, the actual dunes were sampled back in 2011. What newer techniques? The main key techniques would be better cameras, so higher quality cameras, so instead of 25 centimeters. Comparisons between the dune fields on Earth and Mars is key, so continuously checking dunes and seeing the changes and seeing the actual attributes. And the final key bit is also the fact, just look at more dunes, because 97% of the surface still remains unexplored by the satellite. Only 3% has been photographed. So that's the key difference. And yeah, so that's pretty much the end of my talk and a bit of research. So any question, guys?